Hello and welcome to today's webinar from Tektronix. My name is MacLachlan. I'm an applications engineer and I'll be taking you through today's webinar, which is how to design a test system to meet your DC measurement needs. So what will you learn today? So we will concentrate on how to specify your test system and really what the additional steps that you can take to really get the best from your test system. So in addition to the presentation today, at the end I will do a demonstration to go through some really nice tips about how to get the best from your measurement system. Let's get started.
Hello, welcome to this webinar brought to you by Tektronix. My name is MacLachlan and I'm an applications engineer. I'm part of a large team of application engineers, all of whom contribute a wide variety of knowledge and expertise that customers can call upon. My specialities include our Keithley solutions and also RF applications. I support customers both in pre-sales, where I help determine the best solution for an application, and also post-sale support. Part of my job is meeting lots of people working on a huge variety of projects with varying degrees of measurement complexity. Okay, for the agenda today, we will look at a method of breaking down the process of designing a test system into 4 blocks. We will also look at some of the key measurement terms, namely resolution, accuracy, and repeatability. When selecting the appropriate equipment, it is essential to be able to understand an instrument's specifications. We will use an example to explain this. We will also look at the main causes of poor measurement quality in DC systems and what can be done to improve this. Another vital part of the 4-step measurement process is to build and verify the system, making sure testing is carried out in a methodical way. Sometimes overlooked, just because a system works initially does not mean it will still be performing as required sometime later. Vital that the system performance is verified at regular intervals. And lastly, I'll run through a quick demonstration of some of the instrument features that allow for much improved measurement quality. Let's start with the 4-step measurement process. With a typical test scenario, you have to measure some characteristics of a device or material. This can range from a very simple setup, such as using a DMM to measure resistance values in a bench type setup, to more complex systems that involve fixturing and special cabling, etc. Here we have a few examples of instruments. It's always essential to decide how you're going to interface between the measurement instruments and your device under test. You may require some sort of test fixture or a probe station if you're measuring at wafer level, for example. You also need to ensure that you have suitable cables and adapters to connect between your measurement instruments and the fixturing, etc. When working out the required performance of the system, i.e. measurement accuracies and tolerances, etc., it is essential to include not only the performance of the measurement instrument, but also the limitations and effects of the cabling, connectors, test fixturing, and even the environment that you will carry out the tests. So what will limit your test results? When determining how you will carry out your measurements and what equipment you should use, it is important to understand what will limit the quality of your measurements and therefore your ability to meet your requirements. You cannot simply look at the specifications of a piece of test equipment alone and state that using it will meet your overall specifications. It may be that characteristics of the material or device that you're testing will have an impact on measurement quality. The cabling, and if you require a test fixture, will all have an effect on the test results. When looking at data sheets for test equipment, various terms are used as an indicator of quality. Let's cover some of the basic terms and what they mean. Resolution is the smallest portion of the signal that can actually be observed. It is determined by the A to D converter in the measurement device. There are a number of ways to characterize resolution: bits, digits, counts, etc. Most benchtop instruments are specified in digits, for example a 7.5 digit DMM. The half digit means that the most significant digit has less than a full range of 0 to 9. As a general rule, a half digit implies the most significant digit can have the values 0, 1 or sometimes 2. Here we have an example from the Keithley 7510 7.5 digit DMM datasheet with the resolution of each of the voltage ranges circled. Here we can see the relationship between the bits of an A to D converter, the number of counts and digits of an instrument. Often data acquisition devices are specified by the number of bits that the A to D converter has, and counts are the number of different voltage levels that the A to D converter can distinguish between. For benchtop instruments, digits are often used to indicate the resolution. For example, a good quality handheld DMM may have 3.5 digits, whereas the Keithley DMM from earlier has 7.5 digits. The more bits or digits, the better the resolution, and you need to decide what resolution you want to measure to. What do we mean when describing the accuracy of an instrument? We have two types of accuracy, namely absolute accuracy and relative accuracy. Absolute accuracy indicates closeness of agreement between the result of a measurement and its true value, traceable to an accepted national or international standard. Most countries have their own standards institute where national standards are kept. Devices are sometimes calibrated by comparing them to a known national standard value. The drift of an instrument pertains to its ability to retain its calibration over time. Relative accuracy is the extent to which a measurement accurately reflects the relationship between an unknown and a locally established reference value. The implications of these terms are demonstrated by the challenge of ensuring the absolute accuracy of a temperature measurement of 100 degrees C to plus or minus 0.1 versus measuring a change of 0.1 degrees in temperature. Measuring the change is far easier than assuring absolute accuracy to this tolerance, and often that is all that is needed. For example, it's often important in product testing to measure the heat rise accurately, for example in a power supply, but it does not really matter if it is exactly 25 degrees ambient. In this slide we will compare resolution, accuracy and repeatability. The centre of the bullseye represents the target value, i.e. the closer we can get to the centre, the better the accuracy. Here we have three readings with low resolution, low accuracy and low repeatability. Repeatability is the ability to measure the same input to the same value over and over again. In our example, we now have high repeatability, but still low absolute accuracy and low resolution. Ideally, the repeatability of measurement should be better than the accuracy. If repeatability is high and the sources of error are known and quantified, then high resolution and repeatable measurements are often acceptable for many applications. Now we have high resolution with high repeatability. Such measurements have high relative accuracy with low absolute accuracy. Now we have high absolute accuracy, high resolution and high repeatability. This is of course the ideal scenario, but is often the most expensive. You need to decide what is necessary for your test system and budget accordingly. Now let's look at the measurement system itself and how to select the appropriate equipment. How to read instrument specs. A datasheet for a piece of test equipment can sometimes be a little daunting when trying to decide what specifications are relevant to your system. We will look at some of the most important specs. For DC specifications, accuracy is normally expressed in two parts, namely as a proportion of the scale or range that you're on and the value you are trying to measure. For example, It could be a plus and minus gain error plus offset error. It can sometimes be expressed as a percentage of reading and percentage of range error, and sometimes parts per million of the reading and parts per million of the range. The range in this diagram is represented by FS, or full scale. For example, the spec for the Keithley 7010 DMM, when measuring voltage on the 1 volt range, states an accuracy of 30 ppm of the reading and 7 ppm of the range. Here we have the offset error, which is expressed either as a percentage of the range or ppm of the range. In the example just mentioned, the FS would be 7 parts per million of the range. This is a constant error that appears on the particular range, no matter what value you are measuring. Next, we have to include the gain error. This is expressed either as a percentage of the reading or ppm of the reading, i.e. the value you're trying to measure. When we carry out a reading, we can expect the error to be anywhere within the graph, and the error will be a combination of the range error and the gain error. Accuracy specs are normally guaranteed within a temperature range. For example, the 7510 DMM is within calibration temperature plus or minus 5 degrees. If you're carrying out your measurements in an environment where temperatures are out of this range, you need to add a temperature related error. This becomes especially difficult if your temperatures vary considerably. In this example, we are trying to measure 200 milliohms using the 1 ohm range of the 7510 DMM. Using the 1-year accuracy specs from the 7510 datasheet, it is possible to work out the accuracy in terms of plus and minus error when trying to measure a specific value using a specific range. The datasheet states that the accuracy in this example is 50 parts per million of the reading and 50 parts per million of the range. Therefore, the accuracy at 200 milliohms will be plus or minus 60 microohms. What do we mean when we talk about the timing within a test setup? When carrying out measurements, especially in an automated PC controlled setup, it is possible to have fast measurement times. This is especially useful in a manufacturing environment or where many measurements are required quickly. However, care must be taken to ensure that the measurements are taken when the equipment has settled. There is always a trade-off between speed of measurement versus quality of measurement. Now that we have chosen the test equipment for our system, let's look at putting the system together and verifying its performance. Now you have picked the test equipment, cabling and fixturing. It's sometimes tempting to throw everything together and expect the system to perform as required. Very often it is at this point that performance issues arise and it's difficult to ascertain what the causes are. Therefore, it is important to verify the system performance one step at a time. It is usually essential that your piece of test equipment has been calibrated within its calibration period, usually 1 year but can be longer. If you will be carrying out voltage measurements, then placing a short across the inputs of the meter will give an indication of any offset errors. This can be directly compared to the specifications from the datasheet. If carrying out current measurements, then checking to see the current level with the ammeter open circuit will give an indication of offset current. Again, this can be directly compared to the specifications of the datasheet. Now include your cabling and repeat the tests. Now add the test fixture and repeat the tests. Now add the DUT. It's always a good idea to have what are sometimes called golden units, i.e. DUTs that will give known measurement values. Another example is to have some high precision resistors of known value. These can be used to quickly verify that the system is working. As mentioned earlier, timing can be critical when trying to achieve your measurement goals. Cable capacitance, for example, may mean that you need to introduce some measurement delays to your system to ensure signals have steadied and are not charging or discharging the unwanted capacitance. Therefore, you need to check the timing and, if necessary, reassess your measurement speed goals. Insufficient delay times between measurements can often be the source of problems in accuracy and repeatability. This is one of the most common errors in test systems, especially evident when you see a different result when running the test at speed compared to running the test step by step or manually. Inductance can also affect settling times, but capacitance is a more common problem. In a manual system, a quarter to half a second seems to be instantaneous, but in an automated test system, steps are typically executed in milliseconds or less, and even the most simple systems may require delays of 5 to 10 milliseconds or longer to get accurate results. If you find that the performance of the system does not meet your requirements, the one step at a time approach should help identify what's causing the problems. There are many different challenges to maximizing the performance of your test setup, especially for more demanding measurements such as low voltage, i.e. in the nanovolts, low current, less than 100 picoamps, and high resistance, for example in the gigaohms. High quality DMMs are not capable of measuring in these regions due to design limitations. Keithley has a range of specialized instruments such as electrometers, nanovoltmeters, and picoammeters that have been designed to meet these challenges. The Tektronix website has a huge range of material with advice about helping to reduce the sources of errors. The Keithley Low-Level Measurements Handbook is also a valuable source of advice. We'll now look more closely at a number of sources of errors. For resistance measurements, especially lower resistances, it is important to take into account the resistance of your leads. In this example, we're using 2-wire ohms to calculate the resistance. A current source in the meter outputs a known and stable current, and the voltage drop is measured within the meter. This method works well if the resistance to be measured is very much greater than the lead resistance. However, what if the resistance to be measured is much closer to the lead resistance or even less? Using 4-wire measurements will eliminate this problem. The voltage drop is now measured across the resistor instead of across the resistor and leads. The input resistance of the voltmeter tends to be very high in comparison to the resistance to be measured, therefore the lead resistances in the voltmeter path can be ignored. If, however, the resistance to be measured is very high and approaching the resistance of the voltmeter, then it may be that a specialized meter such as an electrometer with extremely high input resistance may be required. Another source of errors are caused by thermoelectric EMFs. In any measurement system, any connections made that are of dissimilar metals will produce a thermocouple. A thermocouple is essentially a device of two dissimilar metals that generates a voltage that varies with temperature. These qualities can be put to good use when using thermocouples to monitor temperature, but in standard test systems it results in unwanted voltages being introduced. As temperatures vary, the magnitude of the unwanted voltage varies. Here we have some examples of the types of voltages that can be generated. Even when connecting copper to copper, there is usually sufficient differences in the metal that voltages will be generated. If the magnitude of these errors are significant in comparison to what you expect to measure, then we do have a technique to eliminate the effect. From the table, it's also interesting to see the potential error when connecting copper to copper oxide. In some of Keithley's measurement instruments, we have a feature called offset compensated ohms. With this feature switched on, the measurement cycle now consists of two parts. First part is to measure the voltage with the stimulus current switched on, and the second part is to measure the voltage with the stimulus current switched off. Subtracting the latter from the former will subtract the errors due to thermoelectric EMFs. The offset compensated ohms feature will effectively eliminate any issues with temperature drift. How can we reduce any errors due to external interference? Noise from electrical power, either at 50 or 60 Hz, depending on what part of the world you're in, will almost always find its way into your measurement system. Keithley has a method for eliminating noise generated from power lines. The most common form of external noise pickup is 50 or 60 Hz power line pickup. The signal components of noise superimposed on a DC signal being measured may result in highly inaccurate and fluctuating measurements. As you can see, our measured value will very much depend on where the measurement is carried out in relation to the sine wave. Keithley instruments have a feature called NPLC, which stands for number of power line cycles, and it allows the user to set the integration period in relation to the number of power line cycles. In other words, a setting of 1 NPLC will result in the measurement being integrated for 20 milliseconds or 1 power line cycle, resulting in the elimination of 50 Hz noise. The performance improvements from this feature are often dramatic. Now that we have covered some of the sources of errors and techniques for minimizing them, let's look at what to do when you are happy that the system is working to your requirements. You're now ready to use the system to gather the desired information. But what you must try and do is regularly run the system with your golden units or reference components, and this will give a very good indication if your system is still performing well or if a problem has been introduced. Also be aware that the specified accuracy of your instruments will vary with time, and therefore you should ensure that the instrument is calibrated on a regular basis. Now I'd like to demonstrate some of the features designed to improve measurement quality and eliminate or at least minimize some of the sources of errors discussed earlier in this webinar.
Now let's do a live demonstration showing some of the issues that we mentioned during the webinar, and we'll show some of the features of the instruments that help you minimize those issues and really hopefully help you improve the quality of your measurements. So let's go over and do the demonstration. So for the demonstration today, what I've got here is a Keithley 7510 DMM, which has 7.5 digits. We have the DAQ 6510 from Keithley, which is 6.5 digits, but also has some switching capability. And we have the 2450 source measure unit from Keithley. And really what I want to do is show some of the features that I mentioned in the webinar, and hopefully you get a good feel for the improvements that you can make when using those features. So for the first experiment, what I have here is a 100 milliohm resistor rated at plus or minus 5%. So in other words, when we measure, we should be able to read between 95 and 105 milliohms. So if we look at the screen here, Just change the range to 10 ohms. We're getting a reading of approximately 159 milliohms. The resistor's rated at 100 milliohms, so there's quite clearly a problem here. So, as mentioned before, the fact that we're doing a 2-wire measurement means that we're actually measuring the resistance of the resistor plus the leads. So that's what's giving us the biggest part of the error. So if I now, let's change it so that we're doing a 4-wire measurement. So if we go connect these leads, and I'm just going to go into the menu and run a saved setup that I had before. Let's run the program. So now what I've done, I've changed it to a 4-wire measurement, and as you can see, the value is approximately 100 milliohms, which is what we're looking for. Now, as you can probably see, it's a fairly noisy measurement, and during the webinar I mentioned the NPLC feature. So let's see if we can improve that. So on the screen here you can see that the integration rate is set to 0.0005 power line cycles, which is the fastest that the instrument can measure. And as mentioned in the webinar, there is always a trade-off between speed of measurement and the quality of measurement. So let's change that to 1 NPLC. And if we come back to the menu, we can now see that it's a much steadier reading. So now we're integrating the measurement over a period of 20 milliseconds. So in other words, we're taking longer to do the measurement, and we're getting a much greater level of repeatability. And as you can see from the graph, if I just change the scale to show all, this is a point here where I changed the NPLC rating, and you can see that there's a vast improvement in the quality of the measurement. So for the second demonstration today, what I really want to show you is a feature that allows you to test the accuracy of your instruments and whether they're still within the spec. So what I want to do is actually short the inputs, the voltage inputs of each instrument. So if I connect these, and what I want to do is to check that the voltage measured is actually less than the accuracy figures that are in the data sheets. So from earlier, in the webinar, we discussed how the accuracy is actually worked out, and a percentage of the error that you would have is based on the measurement. Now, because we are shorting the inputs, that means the measurement part is 0, so we can ignore that. So any errors that we see is now due to the range error. And from the data sheets, I've calculated that for the 7510, we should be able to have an error of less than 9 parts per million of 100 millivolts, which is actually plus or minus 900 nanovolts. If we look at the screen here, we can see that our error is around about 44 nanovolts, so that's well within spec. So again, in a real life situation, that gives us confidence that the voltmeter within the DMM is actually working as within spec. Again, if we do the same for the DAQ 6510, the error should be 0.0035% of the 100 millivolt range, which gives an error of plus or minus 3.5 microvolts. And again, we're certainly around about 10 microvolts. So again, we're well within specification. And the same for the 2450. The 2450 on the 20 millivolt range, there'll be a potential error of plus or minus 150 microvolts. So again, if we look at the spec here, we're well within specifications. So hopefully I've managed to show you some of the features that the instruments have that you can use to improve the quality of your measurements. And that concludes today's demonstration. So that concludes the webinar for today. So let me first of all summarize what you've learned. So number one, we looked at the four-step measurement process for designing your test system. Number two, we looked at looking at the key specifications and key areas that you need to consider when choosing your test equipment. And number three, we looked at the measurement challenges that you might face and some of the key features within the instruments that will allow you to minimize those problems. So I hope you found today's webinar beneficial, and thank you for watching. For more information or to request a demonstration or even for a free trial of the equipment, please visit our website. Thank you.